This is a problem after chapter 7 in the textbook, a very interesting one. Okay, so let's read the problem first. An electron in a television tube is accelerated uniformly from rest to a speed of blah, blah here over a distance of 2.5 centimeter. And we are asked to calculate what is the power delivered to the electron at the instant that when the displacement is 1.0 centimeter. Okay, so now let me move the textbook aside and let's see what information do we have here. So first we know this is about a particle and the particle is one electron. There is something we need to know for the electron. It can be seen as any other particle. It has a mass. The mass of an electron is about 9.11 times 10 to negative 31 kilograms. Very, very small mass for one electron here. So for it can be any other particle. Then we know what? We know it is moving with a uniform acceleration from rest to some distance. So this will treat this as one-dimensional problem. And what we know at t equals 0, okay, and then the velocity is 0. So v sub 0 equals 0. And then we know it is accelerated to a speed of v. So we call that v right here. So that's v F, I call the VF, is given like 8.4 times 10 to 7 meter per second over a distance. So I call that distance that is d1. So this is one particle which starts from a rest, and after it moves along a distance d1, the velocity is v sub f. And we also know a is constant. So we are asked at one specific distance, so at some d2 here, so when it's moving here, at some distance, what is power? P, the power delivered to the electron when it moves to the distance d2. This is the question here. Now let's think about what formula we should be using. So power, if for 1D motion here, power equals the dot product, the force vector, dot, the v vector here. And then because this is the 1D, one-dimensional, and we know it is actually equal to the magnitude of the force applied on the electron or the particle and times v when it moves to the distance d2. So if we are able to find what F is, or the V is at D2, then multiply by those two, we'll be able to get the powers. The power is changing. Why? Because the force is not changing because A is constant, but the velocity is changing at different moments. So the power will be changing as well. So the key is this. First, how do we know the force? Second one, how do we know the velocity at D2? So if we know those two, multiply those, we'll be able to find the power. First one, let's see what is the force. We know what? We know force is equal to the mass of the particle times its acceleration. The problem tells us this is a uniform acceleration. Even we don't know what the value it is, but we know A is constant. So since like for electron, we know M already. Now we need to figure out what the acceleration. So what acceleration we use the knowledge that we are given. We know when it moves a distance d1, we have final velocity vf. It starts from v sub 0 equals 0. So thinking about the formula, like for a constant uniform acceleration motion, the final squared vf squared equals v sub 0 squared plus 2as, or 2a delta x. So this is the formula we had before. Now we plug the value we have here to the formula. So what we have, we know the final velocity is given, all right? Initial velocity is 0. So 0, just ignore it, and equals 2 times a times what? We know the distance it moves is d1. So you keep my symbol here, 2a d1. Now, what can we get? We can find out this constant or uniform acceleration, a equals vf squared over 2d1. So don't rush to plug number n yet. Let's keep simple, find the expression first. After I know the acceleration, now I will be able to find the force. So force equals, now I get the first thing down. Force equals ma equals m vf squared over 2d1. Vf is the velocity when it passes the 2.5 centimeter. Okay, so we got first one, we know f. Now we want to know what is the speed or velocity at the distance d2. Similarly, we use the same formula because we don't know what the velocity at v2, and we assume that is v. So v squared equals what? V sub 0 squared is 0 plus 2 times a times d2. Same formula here for same uniform acceleration. It starts from 0, v sub 0 equals 0. When it moves to the distance d2, the final velocity equals v squared equals 2ad2. Now plug a to the formula. We got 2 times a vf squared over 2d1. And then times d2. Okay, this is the a we got before. Now we got v cancel out, and we can get velocity equals the square root of vf squared times d2 over d1. And because vf has a square, we can move it out, equals vf times square root of d2 over d1. See, we know the force, we know the speed or the velocity at that instant, and then the power when the electron passes the distance d2 equals f times v equals what? Equals m vf squared over 2d1. This is f times v, vf times square root of d2 over d1. Now let's combine because we have the vf squared, we have the vf here, it equals m times vf to the third over what? Over 2d1, take the square root of d2 over d1. And this is the algebraic expression for the power at any distance. So what do we know? We know d1 is fixed. Vf is fixed at any intermediate position. When d2 takes value from 0 to d1, I will be able to find out the instant power at any d2 value. So now, since we are given mass equals 9.11 times 10 to negative 31's power kilogram, and we know Vf, that is the velocity it reaches till the end of d1. What we have the speed of 8.4 times 10 to 7th power meter per second. That's Vf. And what is d1? d1 equals 2.5 centimeter. And let's turn this into meter, 0.025 meter. That's d1. So we get m Vf d1, and then the ratio of d2 over d1. So d2 equals what? 1 centimeter. Okay, so for this one, we do not need to convert this to the meter because d2 over d1, as long as they have the same unit, they can cancel each other. So now plug those numbers into the expression above. We know the power at that moment equals 9.11 times 10 to negative 31's power times VF, which is 8.4 times 10 to 7's power, then raised to the cube. Divide by 2 times 0.025 times square root of, so this time, D2 over D1. D2 is 1 centimeter over D1 is 2.5. See, we have this expression here. Do the calculation. I think the answer in the textbook, we have the final answer, and it should be a very, very small number. Let me check. Okay, so, or we can use the calculator. Do the calculation. It gives a textbook, gives us, go to page 951. And for problem 79, the answer is 6.83 micromu watts. Micro here means 10 to negative 6 power. Yes. Okay, so do the calculation. We should be able to find this value here. And so this one, we can replace the electron by any particle with the mass here, and same way. So basically, it's just combine what we learned before. Use the kinetic information. We found the velocity, we found the acceleration, and then we found the force. If we know the force, we know the velocity, we'll be able to find the power. Okay, so this is the problem, chapter 7. Chapter 7, number 79 in the textbook.